Thank you very much for inviting me. I'm going to talk about other things about the Higgs. So there'll be, I think, a lot of continuity with the first three talks we've heard, and hopefully continuity with what Andy Cohen's going to talk about. I want to start a little bit with history of how the Higgs discovery, how the Higgs mechanism was developed long before the Higgs discovery. It's a very interesting story because it starts with condensed matter physics, and since we're in a material science building, it's always good to give credit where credit is due. So I'll start with the condensed matter theorist Phil Anderson, who in 1972 wrote what I think is a seminal article entitled "More is Different," where he was interested in the question of how come if the laws of subatomic physics are so symmetrical and beautiful, why does the world around us so complex? Which is a very interesting story, and he had a sort of all-encompassing idea about that. But for us in particle physics, the beginning of this is the story of spontaneous symmetry breaking, and of course it was Nambu that really is the father of all this, and won a Nobel Prize for his applications of some of these ideas. But as he said in his Nobel lecture, it's really a fascinating Nobel lecture to read. The title of it is Spontaneous Symmetry Breaking in Particle Physics in Case of Cross-Fertilization. He was living in a world in which a lot of the most interesting things that seemed to be happening were in condensed matter physics, particularly the theory of superconductivity, and that was really his inspiration for the work that he was doing in particle physics. And that's very puzzling until you start to understand his great intellectual leap, which in quantum field theory, you can think of the vacuum, the quantum vacuum, as a medium, which has many properties in common with the kind of media that you have in condensed matter physics. And that really is a great, I think, a great intellectual leap that we're still living off of in particle theory today. Goldstone also was fascinated by what was happening with superconductors. In fact, his famous paper, 1961, which introduced the Mexican hat, is entitled Field Theories with Superconductor Solutions. And he begins the paper by apologizing by saying, this has nothing to do with anything. I'm just interested in this as sort of an intellectual exercise, and then proceeds to do some of the most important theoretical work from the past decades. And in particular, this led to the idea of Nambu-Goldstone modes as a ubiquitous feature of spontaneous symmetry breaking, which of course was a problem because these things are light, they're massless in the ideal limit, and although that's fine in condensed matter physics, it's not fine in particle physics where there's not a lot of massless spinless bosons lying around. Now Anderson came back to this same problem shortly thereafter and said, oh, okay, you stupid particle physicists, look at a real system, look at superconductors where there's spontaneous symmetry breaking of a type you might find very interesting, but where's the Goldstone bosons? They're not there, but there's something else that's happening, which is that the photon is effectively getting a mass, and so apparently these two things must be connected, and you guys should go figure out the details. And of course he was absolutely right, and in 1964, a number of people, including Braun, Claire, and Higgs, did figure this out and began to figure it out. And it's a very subtle story. It involves a fundamental scalar field with self-interactions. I'll come back to that later. Spontaneous symmetry breaking in the vacuum that gives gauge bosons mass, but at the same time it's respecting this delicate choreography that we all have to learn when we learn about gauge theories between gauge symmetry and Lorentz invariance. And it's really quite tricky. It's not obvious how you make all of this work in a consistent way. And I think that really is what this Nobel Prize is about. It's well-deserved on the part of the two surviving members. And then, of course, that's a general statement, and it's not especially interesting until you apply it to something that could be the real world, and that, of course, was the Steve Weinberg and Salam's contribution. And things get more complicated because you now have not just one Goldstone boson, but you have three Goldstone bosons because you have three massive gauge bosons. But then you also get something for free that wasn't really appreciated fully, although it was, some people had thought about this. The fermions also can get mass essentially for free from the Yukawa couplings to the Higgs field. So in the end, what makes a Higgs? Well, it's a spin-zero boson. It also has particular weak quantum numbers. It should come from a complex SU2 doublet with a particular hypercharge. It should couple to W and Z bosons proportional to their masses, to quarks and leptons proportional to their masses. And it also couples to some massless particles, photons and gluons, and it does that through radiative corrections that you can compute. And Maria showed you some of those diagrams. So those are very basic properties of what you call a Higgs boson. Of course, measuring those properties, as we saw, is challenging, and it's challenging in particular because the Higgs decays after about 100 yoctoseconds. Yoctosecond is a very short, it's the shortest period of time for which there's a name. So that's a problem, but Maria showed you how we go about doing that. She also showed you how we eliminated at some level Higgs imposters. The possibility that what was discovered in July 4 of 2012 was not a Higgs boson at all, not a non-standard Higgs boson, but just not a Higgs boson. It could have had the wrong spin, but we think that's probably not true. It could have been a pure CP odd. That does not seem to be true. It could have come mostly from an SU2 triplet instead of an SU2 doublet. That does not appear to be true. It is not the case that you completely rolled out all imposters. You can make dilaton models, you can make spin 2 models that still fit the data, but at some point you should give up on those things. But still, this is not saying that the thing that you have, although I would call it a Higgs boson, it doesn't mean that it's exactly the Higgs boson of the standard model. And that's saying that it can have many non-standard model properties and still be the main culprit of electrical symmetry breaking. So in particular, although it appears from an SU2 doublet, it could come from more than one SU2 doublet. There could be singlets and triplets, SU2 singlets and triplets mixed in there. It could be a CP mixture, which of course would be very important. We don't really know that it's a fundamental particle. It could be a composite. Its couplings to photons and gluons will be different than what's predicted in the standard model if there's other things to go in those loops of those diagrams that Maria showed you. So if it's not just top quarks, if there's superparticles at the top quark, that will change this. If there's extra charged or colored particles, that will change those results. It could decay to exotic particles, for example, dark matter if it's light enough. And in fact, it's really not quite the case that these things couple to quarks and leptons precisely proportional to their masses. That's an approximation, and depending on what all the physics is in there, you'll see small deviations from that if you can measure those properties with enough precision. I think, this has already been mentioned by the other speakers, it's for the LHC, a real critical part of what you're doing in the rest of this program is trying to find other Higgses. We found one, how many more are there? There's good theoretical motivations for this coming from supersymmetry or this generality, but it's very hard to find these things. These things could have TeV masses, they can have suppressed couplings compared to the Higgs that you've already found. So that's going to be, if you did nothing else with the rest of the LHC run, but do your best in finding more Higgses, that would be a very important thing to do. Now you can ask, what do we already know? Well, we found a more or less standard model like Higgs boson. We're trying to nail down its properties with more precision, but there is one property that we know with great precision, and that's the mass, and Maria showed you those measurements. We know it's 126 GeV plus or minus 1, let's say. So what does that tell you, the fact that it's 126 and not some other number? Well, that turns out to be very interesting. 126 is almost the maximally interesting value that the mass could have had. For example, in supersymmetry, this is interesting because supersymmetry predicts generically, that, as I said, that there's additional Higgs bosons. And then the lightest one is the one that we presumably found, although that's not necessarily the case, but that's the simplest thing to assume. And in that case, there's a prediction in SUSY models for what it's, in minimal SUSY models with a minimal Higgs sector, for what its mass should be. And that involves the Z mass, which is in fact smaller than 126. And it involves a cosine squared of an angle, and then involves some radiated corrections, which I've called delta MH squared here. So those radiated corrections have to be pretty large to get you to 126. So we're in this funny position now where, do I have a pointer here? So we're in this funny position now that with 120, if you take the minimal Higgs sector that is allowed in supersymmetry, as gives you the MSSM here with the minimal particle content, at 125, it's within the parameter space of those kinds of models, but it's right on the upper edge. It's suspiciously heavy in that case. There were people that were trying to make, for a long time now, alternatives to this sort of scenario for the Higgs. And there's a popular, well, actually not that popular, but now you have to have something to look at. So composite Higgs models, which involved a different approach, they generically give you something that's heavier than 126, and you can get it down to 126, but it's suspiciously light for those kinds of models. And then there's the question of what it means for the standard model itself, and that Maria already showed you, but I'll talk about that a little bit more. But for SUSY, it's doable, but it's a little bit on the edge. Now, in particular, if you don't want to extend the particle content in your SUSY model, then the way to get 126 GeV to get the big enough radiative corrections is to have large mixing involving the superpartners of the top quark. So that's interesting because once you have large mixing, there's a kind of a seesaw, and it means one of these stop partners could be relatively heavy while the other one could be relatively light. And that's interesting because that may mean that one of the first superpartner we might discover might actually be these stops. Now, if you don't like that, if you think the large mixing is too contrived, then you can do something else in your SUSY model, because SUSY is, you can make an infinite number of models at SUSY, but you have to enlarge the particle content, basically. In particular, you can enlarge the Higgs sector, and it gives you a little more wiggle room to explain this heavier Higgs. But you have to do something, and whatever the something is interesting. It predicts either stops that you should see, it predicts new Higgses that you should see if you work hard. Now I want to talk for the rest of this talk, I want to focus on different connections between the Higgs, having found the Higgs, different connections to other kinds of interesting questions. And I'm not going to be able to get to all of them, but I'm going to try and get to the first few here. So I'm going to talk a little bit about this question of vacuum stability in the Higgs, a little bit about the question of where does the electroweak scale come from in the first place, the possible connection between the Higgs and dark matter, and then a little bit about baryogenesis, the matter-antimatter asymmetry. I won't have time to get to how Higgs talks to neutrinos, which is itself a very interesting question, and I certainly won't talk about inflation and dark energy, although you might have thought there should be an obvious connection between these three things, but I don't think we have a very good handle on that. All of these things, I think that this is the bottom line. You can leave now if you want, because the bottom line of all this is that what this is doing is the Higgs discovery is the beginning of something. It's the beginning of what should be a global experimental effort acting on what in the US we like to talk about frontiers of particle physics that involves high energies, high intensities, and the astrocosmic stuff that we do. And it's because of all these connections, the fact that everything is connected to everything, in principle, through the Higgs. So let me talk a little bit about vacuum stability. This is what happens. Fortunately, you won't see this because it's coming at the speed of light, so don't worry about it. I wanted to start with Michael Faraday because when I was reading, he was one of my scientific heroes, and when I was reading about him, the biographer said that his contemporaries thought he was nuts for suggesting the reality of invisible force fields. And those invisible force fields were things like magnetic fields, for which you can actually have a magnet and it points in a direction and it has a source that you can identify. So now we're talking about the Higgs field. The Higgs field sourcing itself, it doesn't have a direction, it's everywhere in the universe, and so now we're saying this is real. So we're really nuts. But we think that this is indeed true. And in particular, the Higgs field is turning itself on through its own, first approximation, through its own interactions. And that has to do, again, with this famous Mexican-Hack potential, which has this quartic self-interaction with some parameter lambda, which is a dimensionless number. But this dimensionless number, the first thing you do when you start to do this more realistically, is you realize that this number is actually a running coupling. And that means it has distant-dependent quantum corrections, or energy-dependent quantum corrections. Those quantum corrections involve the Higgs coupling to other particles, in particular, especially the top quark, being the heaviest fermion, such that you should really think of this self-interaction as having a scale dependence. We usually express that in terms of this beta function, and the most important terms in that beta function are a piece that involves the coupling itself, squared, minus the top Yukawa coupling, that's why T here to the fourth power. And so there's a competition. You go to some scale and you say, how big is lambda? And then depending on that, either as you go to higher energies, it gets bigger and bigger because of this term, or the top Yukawa wins and it gets smaller and smaller. So there's a lot of other terms about drop here, but that's the basic sort of contest that is happening here. And that energetics is then affecting this question of how spontaneous symmetry breaking works and how the Higgs potential, the energetics of what the Higgs field wants to do, depends on scale. So it's even a little more complicated than that. What I was just telling you here was that there's this Mexican-Hack potential that I can parameterize this way. So now I'm calling the Higgs field phi here. So it's got a mass term, and then it's got this quartic interaction. So I told you that this is a running coupling, so that depends on scale. But also, it doesn't really have this shape because there's again, radiative corrections to the actual shape that involve logarithms. Those logarithms have, this is not really the top mass, it's actually a field-dependent version of the top mass. They have additional field dependence here that's it's logarithms. So it's not really a Mexican-Hack. It's because of radiative corrections. It has a different shape. If I went to two loops, there would be logarithms. So it's a much more complicated story. Nevertheless, the thing you're interested in is what happens when I start to crank up the value of the Higgs vacuum expectation value to very large values. It turns out that you can still parameterize it more or less as some kind of effective coupling here, lambda effective, times an overall Higgs bev to the fourth. And then the question of whether or not there's instability is the question of whether this thing ever goes negative at some high scale. And this was realized a long time ago. There was, I think Sidney Coleman really pioneered the technology of this, but I think Pollicher and Wolfram were the first people to point out that the Higgs could have, even this, within the standard model, could have a built-in instability. And indeed, it appears that it does. If you do just a straightforward standard model calculation, you can do this now at almost at 3 loops. So I have not done this calculation, but we can check parts of it. And what happens is that this effective coupling goes negative at some very high scale, which is sort of 2 to the 10 GeV-ish. But it's very sensitive to things like the top work mass. So what is the actual top that's related to top work mass? You actually care about small variations in the top work mass for this result. If you do this in a cartoon, what's happening is you think you're living in a stable electric symmetry breaking vacuum, but in fact, you're living in a fool's paradise because really, way out here, if you could crank up the bev of the Higgs enough, you get in some kind of runaway instability. And it sort of doesn't matter what's happening as you go further out here. It's really the shape here that's telling you that there's some kind of catastrophic event that can happen that gets you into this other regime. So that's bad, but as Maria said, even if you believe all this standard model extrapolation, it takes 10 to the 100 years, so it's not really urgent to get the right answer to this question. On the other hand, what I think is interesting about this is the fact that you have the sensitivity to the Higgs mass and to the top quark mass, as I said, for very generic reasons. And in the standard model, when you don't assume you put in lots of other junk that would affect these quantum corrections, you're right on the edge of stability. And that's sort of a few percent level statement. And does that mean something? Well, I don't know. Nobody knows. Here's another example that David showed this plot of a few percent coincidence, if you like, where if I put in supersymmetry at the weak scale in order to solve the naturalist problem of the standard model, I get this apparent gauge coupling unification at a similar level of accuracy. But these things are, as far as I know, are not compatible with each other. So one of these is a coincidence at the few percent level. Maybe both of them are, but which one is it? And
sorry, the right-hand side is a cure of the
that is also true. That if you believe this one, then this one is actually stabilized. But then the fact that you were right on the edge now is a coincidence because in fact you weren't right on the edge because supersymmetry stabilized it. So there was no reason why you should have been here. You could have been there, and supersymmetry still would have.
Well, the plot, I mean, the picture is not the same.
Yeah, but that means this is a coincidence.
There is
it means there is no instability, which meant the fact you were within a few percent of the edge was a pure coincidence because you were making the wrong plot.
2% of the wrong.
Yeah, exactly. So the thing that bothers me about this is that I thought that in science that you're supposed to pay attention to things like this and take them seriously, and if I try to take both of them seriously, I have a problem. Now here's another one. And again, I don't know if this means anything either, but you can look just at the beta function of the Higgs self-coupling within, again, purely the standard model and say, well, I'll just extrapolate it up the higher and higher scales and not worry about what happens when I do that. But let's see if anything interesting happens. And the thing that's interesting that happens is that it eventually gets to 0, which for beta functions is an interesting thing for them to do. And where it hits 0 is right about at the Planck scale. So this was a calculation that I did purely in the standard model. Doesn't have the Planck scale input, but there is a calculation I can do where something interesting happens at the Planck scale. So again, if I have the standard picture of how these things work, this is a coincidence because this is not the right calculation to do, and in fact, you usually would do it the other way. You would say the Planck scale stuff that I'm supposed to put in is going to radically change this calculation, so it's the wrong calculation to do. But still, I derived the Planck scale by doing a straightforward standard model calculation. Coincidence. And I think another interesting thing to think about, and not enough emphasis, I think, has been placed on this, is that the standard model has a naturalist problem, which I'm avoiding in this talk because I think Andy's going to cover that. But it has another problem, which I consider just as fundamental, which is that this Mexican half potential that you put in for the standard model, for the Higgs, has a mass parameter put into it, And furthermore, that mass parameter is tachyonic in order to get spontaneous symmetry. So I do not believe that that's what nature did. I believe that this is a smoking gun, that there's something that you missed that generated this instability, some physics that generated this instability. It's not an initial condition. I'm an anti-anthropocist like David, so that's part of my bias. But I just don't believe, I think this is a problem of the standard model that it has a tachyonic input. And furthermore, even if you didn't care that this was plus or minus, you still have the question of where the scale actually comes from. Is it related to something else? So this has an old history that perhaps electroweak symmetry breaking has something more glamorous going on. It could be a radiative instability. It could be generated by quantum corrections instead of just input in the tree level parameters here. So that, of course, is something, as David reminds us, happens in QCD. And you can think about such things happening for the electroweak scale, even with weak couplings, unlike what's happening with QCD. But there's a problem with that, which is that in the standard model, it doesn't work. You can't get a radiative electroweak breaking in the standard model. So if you don't like that feature of the standard model, you have to invent some new physics. And what that new physics is, well, there's many, many possibilities for it. For example, supersymmetry models, even these MSSM models I was talking about, they do that. They have radiative electroweak symmetry breaking. That's one of their nice features. On the other hand, they still have to explain where the basic scale comes from, and I don't think they do that in a very satisfactory way. In fact, I think Steve Weinberg was complaining about that this morning. And another thing you can imagine if you got really ambitious is you could say, well, maybe I can not only generate the electroweak scale radiatively in the sense of getting the tachyonic mass, but maybe I can start with something where there just isn't any mass parameter and generate it from nothing. And various people have been pointing this out for a number of years now. We haven't quite figured out to what extent that makes sense. But I think that is motivation for looking at extensions of the standard model that are not supersymmetry, but are something relatively simple that affects the running, in particular, of the Higgs parameters themselves. And the simplest thing that I can think of to add to the standard model is to add another scalar, which if I want to make it especially simple, I can make it a standard model singlet. So that's what this S is. And then I can couple it to, so now I'm going to use H for the Higgs to distinguish it from the other scalar. And I can couple it in this way so that now there's another, this is again a dimensionless coupling, this lambda SH, usually called the Higgs portal coupling, that couples this one new particle that I've introduced to the Higgs directly through this kind of pi-quadratic coupling. So that's a very, very simple thing to do, but that's enough to already change those calculations that I was showing you for how these things run. So in particular, the only thing I cared about was that instability at very high scales that I was showing you before. This is already interesting because it works in the direction of making things more stable. So that's what I care about. That's interesting. But I can do much better than that if I get a little more ambitious. And what I'd really like to do is I'd like to get into some kind of scenario where now I can get radiative electroweak breaking. So how am I going to do that? Well, if this coupling here, the coupling of the new scalar to the Higgs, is negative, then all I need to do in order to get electroweak breaking is to give this guy a VEV. And then I don't need this term at all. This will give me effectively my tachyonic mass. And then you say, well, that's no improvement, because then presumably I want to get radiative breaking in this, from this guy, and so I've just got the same problem back again. But I don't, because this guy, I don't know what he is. I don't know what kinds of stuff he couples to. I don't know what those couplings are. So unlike the standard model where I knew that I was sunk because I've already measured the relevant couplings, here I don't know. And so for all I know, this guy, even in a very simple picture, could have radiative breaking. And so if you like the holy grail of this sort of philosophy is you'd like to start out with a very simple model like this with no input mass scales and show that you can generate everything from dimensional transmutation without any input scales, but from radiative directions. Now again, the question of whether this makes sense once you start to, if this guy's at the TeV scale, it itself doesn't introduce a naturalist problem. But if I'm worrying about other stuff at super heavy scales, you're still going to have a problem with that unless you introduce supersymmetry. Now, so far I haven't told you what this extra scalar is, but the even more ambitious thing is to say, well, I don't want to just put this in order to explain electroweak symmetry breaking. Let me have it do something interesting. So, for example, this could actually be the dark matter if it's stable, which it could be, or it could couple to the thing that's dark matter. It could couple to some lighter fermions or scalars. You can even have it coupled to a gauge boson that's heavier than it, that could be the dark matter. So there's lots of very simple extensions of this picture that I've showed you where this new field couples to other stuff, and some of that stuff, at least one of those things, is the dark matter. So in that case, we're talking here about the Higgs portal coupling not just to another field, but to the dark sector, to the thing that's responsible for dark matter. So that, I think, is one of the most interesting questions about the Higgs boson. It's a force carrier, as Maria showed you, but is that force actually good for something? And the thing that it might turn out to be good for, I hope everybody knows who this person is.
But Yukawa actually proposed had a vector original.
And also the scale is a little different from the scale we're talking about. So what could that force be good for? Well, it's possible that we know dark matter exists. It's possible that it has only gravitational strength couplings, in which case we're into at least part of David's pessimistic scenario. But on the other hand, it could be a WIMP, which means it has weak interactions. What are the force carriers of those weak interactions? Well, it could be a Z boson, it could be the Higgs, now that we know there's a Higgs, or it could be some new exotic particle. Well, why invent the new exotic particle? This is a perfectly good thing. Let's explore the question of whether the Higgs could actually force the exchange of Higgs bosons may actually be the dominant connection between dark matter and baryonic matter. Well, what's interesting about that is that if you look at these direct WIMP searches, this is spin-independent direct searches, if you assume, contrary to what happens in SUSY, that your dark matter is not a Majorana and a fermion, then in fact the Z boson is already ruled out. Its weak interactions are not weak enough. If it had turned out that the Higgs boson, on the other hand, was 500 GeV, then, well, this could be what's happening, but it would be disappointing because this is way below what they're probing now. It gets you down to things that are going to be difficult to ever probe. But that's not where we are. We're here. And so just by, again, looks like a coincidence of this time of history, if you like, in technology, we are just now beginning to probe with experiments like Xenon doing direct dark matter detection, the case where it's a Higgs boson, 125 GeV Higgs boson that is the dominant connection between dark matter and ordinary matter. And furthermore, I know something about the couplings involved there if I wanted to try to get the relic density to be correct for this dark matter. So there's a blob here because there's some model dependence, but there's not infinite model dependence.
Let's assume dark matter coupled to the Higgs is just
So this is so the extra input that I put in here is that I want the dark matter to be a thermal relic more or less, and with some slop, so that it's not wildly off. Now, as I said, supersymmetry is not a case like this, but in fact, in supersymmetry, which is actually the gray stuff here, it's not the light Higgs, which is the dominant feature in this plot for the direct spin-independent direct detection. It's actually the heavier Higgs, and it actually goes, because of that, it goes further down, just as I showed you here. So that's great. That means that if it really is some simple picture like this, we'll know within the next few years from the improvements of these experiments that something like that could be going on. And as I said, the relic density in this case you can make to work with reasonable assumptions. So my dream, which I don't know if this is my optimistic dream, is that it's going to turn out that there's a relatively simple dark matter sector involving some scalar particle and some gauge bosons and some fermions, so sort of the same kind of stuff that you have in the visible sector. And in that simple model, it's going to turn out that everything is done radiatively. So there is, in this sector, there is a radiative, an infrared, if you like, a low energy instability that causes this guy to develop a VEV. And that, as I showed you, can trigger electroweak symmetry breaking at a nearby scale. So the electroweak scale is determined by the dark matter scale. The dark matter scale is determined by dimensional transmutation. And all the couplings are weak. And then you can, again, address this question of what's happening at high scales where you can have further instabilities or extra VEVs or who knows what's going on. So last but not least, I want to talk a little bit about the connection, the possible connection.
Yeah. Solve the problem of excluding the terms of this symmetry.
I haven't solved any problems. Yeah, I think, it's good to be in a situation where you're at sort of the stage of playing around, but it's not obvious to me how long we're going to stay in that stage. I think that is where we are now in terms of these alternative ideas. So let me talk a little bit about baryogenesis. So we know there's a matter-antimatter asymmetry. It's small, which is interesting. We also know that the standard model has the right ingredients in principle to have produced a matter-antimatter asymmetry. It has non-perturbatively BNL violation coming from sphalerons. It has non-equilibrium conditions, weakly first-order phase transition, and it has CP violations. So that's all great. Those are the conditions that you need. But when you crank the numbers, it's way too small. So that's funny. We had more or less the right conditions, but the numbers don't come out right. So does that mean that the baryogenesis has nothing to do with the electroweak phase transition? Well, I don't know. It could be, because it could be that it's coming from leptogenesis, or it's coming from some more exotic thing that's going to be very hard to test. But what I especially like about this is that this is testable, because it has the new physics that you need to make this work is happening at the electroweak scale, more or less. So if this is the answer, we should know a lot more about that by doing physics, for example, at the LHC and the ILC. So what's the problem? Well, the problem is you need to get a sufficiently strong first-order phase transition, better than what you're getting in the standard model. So there's ways of doing that by introducing extra particles. I also need to get a stronger source of CP violation, so there's ways to do that by adding extra stuff. But that extra stuff has consequences. These new particles have to couple strongly to the Higgs. I can't hide them. They could be things, for example, in SUSY, the stops that I talked about are examples of particles that do this. The new sources of CP violation have to talk to the Higgs sector, so again, I can't hide that CP violation. In fact, it's already very constrained by these searches for electric dipole moments, so maybe we're gonna turn up with an actual EDM positive result in one of these EDM searches. And again, the most optimistic scenario, this is all connected to the dark sector, because I could turn out that the dark sector, what we're seeing is not a thermal relic, that it actually has its own asymmetry, and that asymmetry is related to the baryon asymmetry, which might explain the fact that the dark matter abundance is not 1,000 times different than baryon abundance. So all of this, whatever it is going on here, if this is what the answer is, it has to do with things that you can go out and look for in experiments. In fact, there's even something here that makes very happy, because eventually there's a gravity wave signature that you should see. So that's almost the end of my talk. Again, I want to emphasize this question of Higgs connections. You find the Higgs boson, you're measuring properties of the Higgs boson. It's because I'm interested in the Higgs boson. But I'm especially interested in all these connections. And look at all these connections. This is incredible. All this stuff here is all, even the one that's crazy, even the stuff that's crazy is actually very plausible in the sense that, this is a scalar that has a spontaneous symmetry breaking. This seems to involve scalars. This might involve scalars. So even the crazy stuff is plausible. And then there's the stuff that I know that there's things that I have to answer here. And then there's the stuff which it may or may not be true, but if we're going to know within a few years if we're on the right track. So I think this is an incredibly exciting prospect, and it all has to do starts with understanding what's going on with the Higgs. And so I want to end on that note, because to me, again, if you like, it's a historical coincidence that we now have on the launch pad a collider that is exactly the thing you want if you've discovered a light Higgs. And this is not entirely a coincidence. In fact, I think Maria mentioned this fact. When we first started doing ILC physics studies, we did them for 125 GeV Higgs, because that was the most interesting case for the ILC, if you were lucky enough to find 125 GeV Higgs. Well, that's what we found. So in terms of things that we actually know for sure, that is that there's a Higgs and what its mass is, we're in the best case scenario for the ILC. And to me, it's incredibly exciting that we can actually get going on this, and I don't have to wait another 2 lifetimes in order to do the things we need to do to answer some of the questions I showed you on the previous slide. Thank you.
Questions? Could you show me again the page 46?
Yes.
I have 2 questions. One is, what symmetry prohibits mass terms of the potential?
There's no symmetry that prohibits mass terms in the potential, except that if you set the mass term to 0 at some scale, and then compute gradient corrections from that, the mass term will stay 0. So it's self-consistent in that sense. The question of whether you can make a symmetry argument that has to do with the usual naturalist problems that would come if you combine this with a theory that had much higher thresholds, that is not solved in what I'm talking about. In ILC physics is to make sure that we didn't miss something that has to do with neutrinos at the TeV scale. And we are not there yet. That is something that we can do in principle, but we're not there yet.
Any questions? Okay. If not, let's thank the speaker once again.